Yeah. 1 second. Yeah. Right away. Make it correct. Being on the right. Like straight up. And I wrote it, now first one guys, you can have more than 3 resistors or less than 3 resistors in a circuit. I just use 3. Is everybody clear?
Did you say
you can, yeah, you can have 1, 2, 3, 4, whatever in a circuit, okay? I just use 3 all the time, or most of the time, okay? And I also showed you, when you draw a circuit like this, in other words, you have the power supply and then the resistors, okay? Voltage in, voltage out. Voltage comes out in the resistor. These are all equivalent circuits. This same thing as that, that's the same thing as that, okay? Because the electron doesn't know there's a bend in the wire. It makes no difference to the electron, okay? And that's why I want you to understand, don't get fixed on one look. They all mean the same circuitry. And this is, once again, R is in series. The resistors in series. These are the schematics. Schematic just means electrical drawing. Where's your paper hose at?
Are those like equal signs?
Yeah. We're just trying to say all those are equal. They're the same thing. The wires are bent different, that's all. The electrons do not care about that. Were you actually waiting on me to tell you to take notes? You guys know it. I don't take a grade on your notes, do I?
Nope.
You don't take notes. If you can get by with it, fine. If you can't, and most kids can. You know, make sure it's too good. All right, guys. Let's get her down.
Oh, LeBron. I meant to say LeBron.
Let's scroll down a little bit.
Nope.
These are very complex.
I'm going to go over that, but it's down here in the rest of the notes. The minus means anytime the small bar means like it's a battery, okay, or a power supply. This means the negative pole, the positive pole, just like you have on batteries, correct?
What are those little lines?
The long bar is always the positive. The short bar is always the negative. Now what?
What are little lines next to like?
These things here?
No.
What?
The one below the.
This?
Equal.
You're talking about this?
No,
Oh,
all those are equal?
I'm just saying that circuit equals that circuit. It's the same thing.
Equal to that circuit, which that circuit is equal to the first circuit.
Yes.
Yeah.
Everybody good?
Yeah.
Next area.
And all I did was the wire's bent different than that, but the current does the same thing. I mean, I would think that's fairly obvious, but if I don't do that, I guarantee you some kids don't get it. Can I scroll down now? Say when. Does everybody have this one?
Yep.
No.
I'll do something. No.
Oh, wait, you I felt like I was John Trek. Somebody died and then came back to life and died.
Oh.
Thank you. All right. said was here, guys, and I should have put this at the start. A resistor is that's how we draw a resistor. That's how we draw a power supply. Power supply can be a battery, an outlet, and a power supply, which I have when you make circuits next year. In other words, it's a source of voltage.
Is that 1 over T?
Do what?
No.
Oh, no, never mind. Okay, I get what you do.
No, it's not 1 over T.
I know this side.
Yeah, except I said it's the power supply. That's how we draw it. Other than that, it's 1 over T.
Yeah.
All right.
It is 1 over T.
Well, yeah, how'd you guess? Write that, and then we'll stop here and we'll talk about this stuff just a little bit, okay? Aaron,
Yes, sir.
give it a rest. And for the most part, these things are self-evident. It's that circle there with the arrow, that's the direction of the current. In this case, it's clockwise. This current is in the direction of the positive flow. Bless you. Okay? How do I know that the positive flow goes that way? Positive charge tries to find negative charge, doesn't it?
Yes.
There you go. That's how you know. Anything I want to say about that? Let me check something real quick. Nah, we're going pretty good. I told you everything you need to know down to this point right here. I do want, let me stop that. Let me stop, and I need to do this, show you this. That series circuitry, the resistors are back to back to back, right? I've already shown you series. This is parallel. Here's the battery. And you can do this in different ways. I'm going to do it this way. Call this R1, this R2. And I need to, just for a second, make sure that this is on film, which is not. There you go. Now, I want you to look at this circuit and compare it to what that other was. And the other, and this one right here, whatever current goes through, the battery also goes through each one of these resistors, doesn't it? Right?
Yes.
But look at this. The current splits, doesn't it? It comes here from the battery, then it goes here, and some goes here, doesn't it? We call that parallel. It splits, comes back together. They're parallel. These two are parallel. But if they're back to back to back, they're in series. Everybody clear?
Is there an equal amount that goes that way and that way?
Huh?
Is there an equal amount that goes down and up?
No, if that resistance is the same thing as that resistance, then that current is the same thing as that, but that's usually not the case. Think about it. This is all the current, then it splits. If this resistance is more than that, then more current goes here, doesn't it? The path of least resistance. And essentially, you can look at this like water pipes. The narrower the pipe, the more resistant. You know what I mean? The less water flows. All right. Now, Chad, I just want to make sure you have the concept down. And we're not doing parallel today, but you need it. All righty. Now, well, yeah, you can think of that way. Only, and I'll leave it there. That's good enough. But there are different sources of power. The battery's one, the outlet's one, and I have little boxes that are power supplies. They produce voltage. You know. All right, guys. Now down here, yes, we said current's going to flow that way from the positive to the negative pole on the battery or the power supply.
Always?
Yeah, always.
Just making sure.
Now, for R's in series in a circuit, as you go around a circuit, the voltage in voltage in, we do this. The voltage in must equal the voltage out. I really should have looked. Well, never mind. We'll see. Now, as voltage goes into the battery, it comes out the resistors. In other words, you're putting joules per coulomb in at the battery, you're getting joules per coulomb out at the resistors. That's what we're saying. conservation of energy. And right, this other stuff, we'll go over it all in just a minute. Oh, mercy. Can you picture electrons traveling in circuits, by the way? Well, it's hard to see what they do, right? The electrons move through a circuit. I mean, the biggest reason why you believe electrons there is because you see them in action, electrostatic forces. Something's at you. You rub your feet on the carpet, you smack somebody on their ear, just barely touch them. Don't you love it to your mom? When she's reading, wow. But electrons are there by seeing the effects of it. Everybody ready? Now let's look at this, make sure we got it. This is for in series, resistors in series. As you go around this circuit, voltage in must equal voltage out. What we're saying is, voltage comes in here, let's say this is 10 volts. Then you drop some volts here, you drop some volts here, you drop some volts here, right? You gradually drop 10 volts, don't you? Everybody clear? All right, good. Let's keep going. And all it says the current is the same in all the resistors. Whatever's the current through here must be the current there, there, and there, right? Because it doesn't split anywhere, does it? Everybody clear? And I said voltage in equals voltage out here. The voltage in the power supply equals V1, V2, V3. V1, V2, V3. All right, now to do this, guys, there's a definite equivalent resistance. It's a definition. You did pretty good on that thing yesterday. Right now you're anywhere from a middle to a high 4. But if you go over all this stuff, you get a 5. And that's pretty good for covering it all in 1 year, you know what I mean? That's a bunch to cover in 1 year. As a matter of fact, it was the highest grade in class. Chase real quick. We'll do this. Now, right when you finish writing that, I will tell you what I mean for sure by that. Make sure you know. Before I even tell you what I mean by that, you have an idea what I mean. I'm sure Jose does. He's thinking about intensity. Right, Jose? Oh, yeah. And Esteban as well. What does that mean? Zoning in, aren't you, Esteban?
Sure.
All right, everybody ready for this little spiel? Here's what we mean. Here's what this means. In other words, if I want to get the same total current, I can replace all of these with one resistor. It has an equivalent resistance. Therefore, if it's the right resistance, the total current in this will be the total current in that circuit. Does that make sense? Is that clear enough?
So all of those three equal the same resistance
Yes.
as that one?
This is the equivalent resistance, all three of these. Therefore, this circuit, as long as that voltage is the same thing as that voltage, then these both circuits will have the same total current. Okay? That's it. Now, let's do equivalent resistance then for a series. That right there. Let's do that right here. There's your equation for equivalent resistance. This right here. Never mind that for the time being. I didn't have enough room is why that happened. REQ for series is R1 plus R2 plus R blah blah. How many R's did you have? So in series. REQ means equivalent. Equivalent resistance. Now scroll up some of the guys, but don't write what's under there just for the time being. This is an example problem, okay? Don't do the one in the book, although theirs is just as good. Now you got that, guys. Here's the example problem. I have a 3, 4, 5 ohm resistor in series with a 12 volt power supply, okay? And I need to get rid of those. Can I do this without messing things up? Yeah, I can. Okay. And if I do the equivalent resistance of this, I get 12 ohms for an REQ, don't I? Because 3, 4, and 5 is 12. So those two circuits are equivalent. And let's say I want to get the total current. How do I do that? I'm going to use this one right here and say, I know voltage in equals voltage out, right? 12 volts in, 12 volts out. That means I get 12 volts out of this thing right here. So here's the equation I used to get the total current. Voila, V equals IR. In this case, it's V I total equals REQ. Excuse me, V equals I total times REQ. Is everybody clear on that? My REQ is 12, right? So I isolate the I total, and I get V divided by REQ equals I total, 12 divided by 12, 1 amp. That's my current, my total current. You always use the REQ to get your total current. Do one more thing with this, and then we'll set you guys loose. Once, guys, the whole lesson there was how do you get the total current? Get your REQ, then do V equals IR, where V is the voltage of the battery because voltage in is voltage out at REQ. Everybody good? All right. Now, the last thing I want to do is up over here. My parallel circuit. Well, let's get the voltage drop in every resistor. And there's an interesting result here. I'm not just doing this for fun. What's current in I1? What's current in the R1 resistor? 1. It's 1. What's the current? What's I1? What's the current in R1? In this R1 right here. I'm calling it R1, R2, R3. And you know what? That was a dumb way to do that. Because I'm not, here, guys, I'm going to change that. I did the other trees that way. Because usually I call this R1, R2, R3, right? But I'm going to do this. I'm going to change the subscripts to match the resistance. You follow me? And that's what you should do. This is, some call this V3 for the 3 ohm resistor, I3, R3. And this is going to be 4, 4, 4, 5, 5, 5. Does that make sense?
Yeah.
Now, what's the voltage drop in the 3 ohm resistor? What's I3? Well, it's 1 amp, isn't it? How do I know that? Yeah, we got the total current is also the current through every resistor. It doesn't veer off anywhere, does it? All right. This is going to be 1 amp times 3 ohms. And how much is that? Was 3 volts, right? Okay. Let's see the other two. This is 1 amp times 4 ohms is 4 volts. 1 amp times 5 ohms is 5 volts. Now, by the way, one kid asked me, says, "What is the RQ? Or, excuse me, is the total current always 1 amp in every circuit?" Of course not. Okay. All right. So, guys, now if you add this up, what do you get for the total voltage drop? Does that make sense to you? It should. Look,